Hey, welcome back. In this video, we're going to talk about finding the area of polar regions using double integrals and polar coordinates. This is a little bit different than what we've done previously with double integrals and polar, because what we had before were these two variable functions that we then translated the projection onto the xy plane into polar coordinates. This is you're actually just given the equations that you've seen in your life previously in polar coordinates. We're just going to compute the areas with double integrals. Our setup here is pretty dang straightforward. What we have is our area described here. We have our theta values, A from alpha to beta. That's the one thing where we have to do a little bit of algebraic work to figure out those values. We have our R determined by these bounding functions right here. And that's always going to be the functions that you're using to define the space that we're looking at. And then again, nothing's really crazy here. It's all that what you come to expect. We have our region. Here we have our alpha and beta for our change in theta. And we have these variable functions that describe the change in the radius. And then importantly, again, don't forget about that r, dr, d theta, which is that change, that small area. In this specific example right here, we're being asked to find the area of the region in quadrants 1 and 4 outside of the circle r equals the square root of 2, and then lemniscat r squared equals 4 cosine of 2 theta. Just to make sure you have an idea of these two shapes, you've seen these before, or things very similar to this. What we have is this circle, and I won't label this in all its great detail. We have this circle right here centered at the pole or the origin right here, and we have this lemniscat that runs something like this. It's just this infinity looking thing. For this specific example right here in quadrants 1 and 4, we're looking to define this region right here. Our first job is going to be to find these points of intersection, which are actually going to be theta values that will describe this alpha and this beta. In order to do this, we simply set these equal to each other. A little bit awkward since we have an r and an r squared here, but actually make our lives a lot easier if I just write this as r squared equals 2. So now I can set these equal to each other to find their point of intersection. So I have 2 equals 4 cosine of 2 theta. Divide both sides by 4, I get 1/2 equals the cosine of 2 theta. And then here, I'm going to apply the cosine inverse to both sides. I'm going to use the trick because of this nature that I see here. I want to know this angle and this angle right here. I know that the cosine is an even function. I get this plus or minus out. So I'll just show that step right here. If I apply the cosine inverse to both sides, what I'll get is that 2 theta equals positive or negative the cosine inverse of 1/2. The cosine inverse of 1/2 is pi over 3. And then dividing both sides of that by 2, I get that theta equals plus or minus pi over 6. And going to my picture right here, this is negative pi over 6, and this is positive pi over 6. So this will be my alpha and beta range for my theta values. And then something else a little awkward. It is a bit awkward because they're giving us an r and an r squared here. We dealt with that by squaring that, but I actually want to use this as my first function, which is r equals something in terms of theta usually, but this is a constant r which produces this circle. But in this case right here, I need this in describing this region to be r equals, not r squared equals some stuff, right? So I want y equals something in terms of x usually. We're describing functions. I want this to be r as a function of theta right here. The good news is I actually can take the square root of this and not screw anything up, is because within this region of theta values that I'm working on right here, the cosine will only output of a positive value. It's a really important little trick right here, but it's set up to make my life a bit nicer. So instead of the r squared equals 4 cosine of 2 theta, and to get this in terms of r, a function of r in terms of theta, what I can do is just take the square root of both sides of this, knowing that this cosine is only outputting positive, so I don't need a plus minus in this scenario right here. So I'll get 2 square root of cosine of 2 theta. So I have my inner function right here and then my outer function right here. which are important. This g of x and h of x are the lower bound and the upper bound here for my r values. So I can calculate my area. My region here is from negative pi over 6 to pi over 6. My bounding functions for the radius here. So this is my lower bound of the square root of 2, and my upper bound for the radius is 2 square root of cosine of 2 theta. And then the beauty is I don't have a function that gets plugged in here. This is just r dr d theta. Though you'll find interesting is that now that actually r can be thought of as this function because it is a factor, a variable factor in terms of r right here. So now what I'm going to do is evaluate this first in terms of r. So I have negative pi over 6 to pi over 6, and I'm going to have r squared over 2. That's the integral of r in terms of r. And now I'm evaluating at these bounding functions. So square root of 2 and then 2 square root of cosine of 2 theta d theta. And then I'll plug in my upper and my lower bound here for that first integral. So let me write this in, negative pi over 6, pi over 6. So when I plug this in for r squared, what I'm going to get is 4. That square cancels that square root, which I should have written all the way over there, is the cosine of 2 theta. So that's that squared divided by 2 minus, now if I plug this in, what I'm going to get is r squared, so that's 2, so 2 over 2, so that would just be minus 1. And now we're going to do d theta, and just for kicks, I'll reduce this real fast, so that will end up being 2 cosine of 2 theta, and then minus 1, so that's my new function right there. Evaluate this in terms of theta. Nothing too difficult here. 2 cosine of 2 theta, that actually will integrate into just sine of 2 theta. Again, doing a little bit of mental U substitution right there, but you could always differentiate that. Does sine of 2 theta with the chain rule become 2 times cosine of 2 theta? Heck yeah, it does. Minus 1, when I integrate that, I'll get a theta, and I'm evaluating that at pi over 6. From negative pi over 6, to pi over 6. And then evaluating this, and again, I'm assuming that you feel really comfortable with your trig values, especially on the unit circle. What I'll get here first, when I plug in pi over 6, 2 times pi over 6 is pi over 3. So the sine of pi over 3 would be the square root of 3 over 2 minus theta, which is just pi over 6. And then the lower bound, when I get negative pi over 6, I'm going to get negative pi over 3. Negative pi over 3 outputs a negative root 3 over 2, and then minus theta again. So that's minus, and then negative pi over 6. Just cleaning this up real fast. Let's see, those turn into a plus right there, but then that negative distributes. That negative will make that a plus, and it turns that back into a negative. It's kind of ridiculous how I'm writing this out, but we're just going to go with it. What do we get? When we put this plus that, so root 3 over 2 plus root 3 over 2 gives us a root 3. And then we have minus pi over 6, and that was a minus pi over 6. So we have minus 2 pi over 6, which is minus pi over 3. All right, and I went through that evaluation pretty quickly, but I'm sure if you paused it, you could double check all of that work. The real emphasis this is just saying, hey, we have this ability to calculate the area of polar regions with these double integrals. We have this function value that is just 1, so it's the same equation for finding these volumes, but we just have our function be 1. Don't forget that we still have this factor of r that really comes into play right here. In fact, if you paused, you could look back at previous conversations, probably in a previous class when you found about calculating the areas of polar curves. Because of that one move right there, we get this 1/2 r squared. That's actually the equation that we developed previously. So we kind of, each of these methods are exactly the same. But the real work here is finding your bounds for theta. Make sure you're paying attention to the description, not just solving the equation. These polar or these equations that include trigonometric functions can have like multiple different solution sets on one unit or one trip around the unit circle or from 0 to 2 pi. Make sure you have the ones that you're looking for. Once you have that, make sure you can identify which is the lower and upper bound, and make sure when you're looking at that, the upper bounding function is the function that outputs larger R values or is further from the pole. The lower bounding function is closer to the pole. But after that, the work is pretty straightforward. Just doing your integration. 2 steps, obviously, for the double integral, knowing some stuff about the unit circle, and getting your final answer.